All right, we left off last time doing some basic stoichiometry problems, and now we're going to ramp them up by setting up a problem like number 25. And before we left, I asked, how was this problem different than the problem before? And you guys said, oh, there's two reactants, so in order to figure out what's in excess, we need to figure out the what? The limiting reactants, or reagents, either's fine. I'll write reactant too so people don't freak out. Either one's acceptable, and you'll hear them both a lot. So there are some steps. I know Ms. Rozier does this as well. We have our way of doing limiting reactants. You might have learned it differently in regular and even in pre-AP, depending upon what teacher you had. Really don't care how you do it, but I truly believe this is the quickest way. And I think Ms. Rozier feels the same way. So dividing by coefficient. Okay. So the steps to doing this. The first thing that you have to do before you can do the problem is get both of your reactants in moles. So you need moles of reactants. So depending upon what they give you, in this situation for problem 25, we're like living large because we're already in moles. That's done. And the next thing you want to do is divide by the coefficient in the balanced equation. And why do we do that? I always like to use the sandwich analogy. Let's pretend this reactant is bread, and let's pretend this reactant are pickles. Let's just pretend, okay? If I were to have a certain amount, a number of moles that I bought from Costco, and I knew that this sandwich to be made appropriately needed 2 slices of bread and 7 of those little round pickles, I could figure out which one of those is going to cause issues and which one's going to run out first. If I had like a big loaf of bread and say I had 500 slices, okay, and then I had a jar of pickles that maybe only had 100 pickles in it. The reason we're dividing by the coefficient in the balanced equation because that's telling us how much bread and how many pickles we need per sandwich. So here, 500 divided by 2 is 250. What is that telling me? I can make 250 sandwiches. I can do the reaction 250 times. Here, 100 divided by 7, a lot less, right? So that, in this case, that would be my limiting reagent. So by dividing moles, it has to be in the same unit, by the coefficient in the balanced equation, I can figure out what's going to run out first. Yes? I think that's in the problem here. Yeah, and I'll revisit that when we get to the problem. So the third thing you would do then is say that after you do the division, the smaller number is the limiting reagent. So we never use how many sandwiches we could make. The 500 divided by 2, making 250 sandwiches, we'll never use that 250. That number is just a mode of comparison to figure out what's going to run out first. And now we'll do this in chemical terms. Here it says determine the moles of CO2 and H2O when 2 moles of ethane are reacted with 10 moles of oxygen. All right, so in order to do this, the first step is to find the limiting reagent. Once I do that, I can do stoichiometry to find moles of my products. So let's start with the ethane. Moles of reactants, number 1, done. Okay. Then I take my moles of each reactant and divide by the coefficient in the balanced equation. What's my coefficient of ethane? 2. So I get 1. And I'm just going to write 1-ish because, again, this number is not a number I'm going to use. And then I have 10 moles of O2 divided by 7. What is that? 1 point something-ish, right? I don't care what it is. 1 point something-ish. So I know that's bigger than this. So what does that make this? This is the limiting reactant because I've got more of this at the end. I can do this reaction once. This reaction I can do more than once. So this is limiting. And what I do on my equation, if it's an excess, I put an X on it because it's an excess. So now I just do stoichiometry. Here's the thing about stoichiometry I want you guys to really pay attention to. I could go from here to here, here to here, here to here. Stoichiometry doesn't have to be reactant to product. It can be product to product, product to reactant to reactant, whatever. In this particular case, this ethane is the limiting reagent. I'm going to go ahead and solve for moles of carbon dioxide using stoichiometry. So I'm going to start with my given moles. I've got 2 moles of C2H6, and I'm going to stoich. Let's do CO2 first. Can I go on the mole bridge now? Yeah, I'm in moles. So for every 2 moles of C2H6 I have, how much CO2? 4 moles. And this is a great problem, CO2, because they're asking for moles of product. I don't even have to go to grams. So how many moles of CO2? 4.00 moles. Now, I can stoich, I got to get moles of water. I could start from the ethane if I want, or I could go from carbon dioxide to water. It doesn't really matter. I tend to always like to start back at the original. 2 moles of C2H6. For every 2 moles of C2H6, how many moles of water? Oh, it's 6. I thought it was 4. 6 moles of H2O. So how many moles of water? 6 moles of water. Okay? Now let's move on to one that's a little bit more realistic. You rarely are going to be given moles and then asked for moles. This was just to kind of introduce the concept. So let's look at the next one. Calculate the mass of calcium nitride formed. So we're looking for grams of calcium nitride when 50.0 grams of calcium are reacted with 50.0 grams of nitrogen gas according to the reaction. I'm going to stoich over to calcium nitride from one of the 2 reactants, but what do I have to do first? Find the limiting reactant. So to do that, I need to convert both to what? Moles. So I'm going to kind of do a little mini chart again because I'm a big fan of the little charts. So I've got 50.0 grams of Ca. For every 1 mole of Ca, I have, and get out your calculators, I need you all to be busting out with the calcs, 40.08 grams. All right, so how many moles of calcium? Louder? 1.25 moles of calcium. All right, nitrogen, 50 grams. For every 1 mole, I have, it's a diatomic, so that's 28.02 grams. 1.78 moles of N2. Okay, now what do I do to figure out what's going to run out? Divide by the coefficient. This is a 3. I'm assuming that's the equation's balanced. This is a 1. So this gives me like a point, what? For 1-ish. And this is a 1.78-ish. So which one's going to run out first? Calcium. So this is an excess, and I can do stoichiometry from there to there. So I'm going to start with my given. Now remember, we did calculate that number, correct? So if I wanted to, if I really wanted to, rather than starting at 50 grams again and putting it in my stoichiometry, since I already did the work, are you guys okay if I start with 1.25 moles? All right, so 1.25 moles of calcium. All right, I'm on the mole bridge now. For every 3 moles of calcium I have 1 mole of calcium nitride. And then I need grams though. So for every 1 mole of calcium nitride I have molar mass. Anybody? I know somebody has it. Come on, guys. 148.26. All right, those are my grams of calcium nitride. So to 3 sig figs, how many grams of calcium nitride did I produce? 161.8 grams of calcium nitride produced. There we go. Oh, roll back. I'm adding on to the problem. I'm going to add on to this. I'm going to ask you another question. How much nitrogen is in excess? Huh. Any ideas what we're going to do here? Nitrogen was extra, right? It's in excess. They gave us 50 grams. The question is, how much was extra? How much is going to be sitting there unreacted? Any ideas? Okay, figure close. Subtract the 0.41. I mean, you're getting the subtraction's correct. That's the big idea. Trevor? Okay. Yeah, we're not doing that. That's a lucky coincidence. But no, we can. What if I would have had another product there, and you couldn't have done it? So he's trying to be tricky, but there's a common way that you can do it that works. Noah? We have the grams of both, but no, we can. That's kind of what Trevor was saying, but that's only because we know the total grams of our one product. If I would have had another product here and you didn't know that total, you can't do that subtraction. So I want to give you a method you're going to be able to use all the time. Okay, that was a lucky coincidence. Johnny? Via stoichiometry. That's what we're going to do. Remember, you can stoich back and forth. We can figure out using this grams, how many grams, or we can go from here to here. Which way do you want to go? It doesn't matter. Okay, we're going to go from calcium then to grams of nitrogen. That's how much is used. And then we could subtract and see how much was left over. Okay, so I think some of you were leading to that, but you weren't getting me the right terminology. So we're going to start with our calcium again, our 1.25 moles of calcium. For every 3 moles of calcium, I have 1 mole of N2. And then for every 1 mole of N2, I have 28.02 grams. This is how much nitrogen was used in the reaction. What does that turn out to be? 11.7 grams. All right, that's how much is used, but that doesn't answer our question. Our question is how much is in excess? Well, we had originally 50.0 minus 11.7, 38.3 grams in excess. Y'all understand it, the concept. Don't forget the stoichiometry. Okay, so I get to pick on somebody today. Who is it going to be? I'm going to pick on Noah. Every time I say Noah, I want to talk about an arc. And I know that's horrible. We already kind of talked about this. I know. You're really you built it? You're really the only person I know other than the biblical Noah. That's like all my years of teaching, you're my first Noah. Your parents were smart. Okay. Anyway, so what we're looking at in this problem, the first is a limiting reactant question. Then we get into something theoretical, then into something called percent yield. And seeing this ahead of time, I want to go ahead and define percent yield to give you the big picture of this problem first. So percent yield is a number that tells us how good of a job we did in the laboratory, basically. How much we produced and compared to how much we should have produced and how much we made and if that's good or bad. We're going to say this is Noah's experiment. And we need to figure out what Noah's percent yield was. To find percent yield, we would put the amount Noah actually got in the lab, the amount of solid he actually produced, since this is a solid in this case, divided by how much he theoretically should have had. Actual, sometimes people call it experimental. So Noah did the lab, and he produced X number of grams, physically made it. That goes in the actual. Theoretical yield is what he should have gotten. So let's talk about calculating grades. Theoretically, what should you all get for your grades? 100. If I want to calculate the percent of your production of grade, how do you do it? Say like Lincoln got a 92. 92 over 100 times 100, doesn't that give him his percentage grade? And that's what this is. Actual is what they actually get. Theoretical is the perfect world. And theoretical, to find theoretical, it's always what you get from the math. You always have to do stoichiometry to get your theoretical. So anytime you see theoretical, I want you to think, oh, I have to do math to find that out. So let's start this problem. It says if 2.50 grams of AS2O3 and 4 is mixed, and the reaction proceeds to completion, which is the limiting reagent. So that's its own problem. I'm going to go ahead and write the grams under each of these because, again, I don't want to have to read this every time. And I've got my grams now underneath each, and I want to figure out limiting reactant. So easy. Do a little chart here. I'm just going to split this into 3. And so for every, I'm going to start out with my 2.50 grams of AS2O3. If I'm doing limiting reagent, what do I want to convert that to? Moles. So start calculating away. To save some time here, first 2 rows, you guys do the moles of AS2O3. These 2 rows, I want you to do the moles of I2. And these last 2 rows, I want you to find the moles of water. And I'm going to put the video on pause while y'all do this. So what is the molar mass of AS2O3? Molar mass. And you got moles of 0.02. Can you give me a couple more? 0.020 moles of this. All right, I2 people, for every 1 mole, how many grams do I have? All right, Lincoln, and what's the moles? Well, that's a big difference. Oh, you said 1.18, 0.018. Okay, that's not a big difference. And then we have 18 grams per mole here. Last group, what did you get for moles? Okay. So now we have the moles of all 3. So it looks like I can officially give Noah a hard time because he gave me the wrong molar mass. He's getting humiliated on the video. I'm just teasing. Okay, what was it supposed to be? 197.84, giving us moles of 0.0126 moles. Okay, so now that we have the moles, the next step in the limiting reagent issue is to divide by, we're not doing empirical formula, we're doing limiting reagent, coefficient in the balanced equation. So this is divided by 1, and this gives us 0.0126-ish. This is divided by 2 and gives us 0.00-ish. And this is 0.11 whatever-ish. Right. Which is the smallest? I2. So this is going to be my limiting reagent. I just care about this number. This is my limiting reagent. This is in excess, and this is in excess, so I don't care about it. So I2 is the answer to A. Part B says, calculate the mass of AS2O5, which is theoretically possible. What should we get if you do that equation or run that reaction in the lab? How much should we get? Well, now that we know the limiting reagent, what do? Stoich on over on the mole bridge. I have my moles here. I could start with grams if I wanted and go to moles, but I've got the moles, so why do it again? Moles of I2. Okay, for every 2 moles of I2, I have 1 mole of AS2O5, coefficient in the balanced equation. And then for every 1 mole of AS2O5, I have how many grams per mole? 229.84 grams. All right, that should give me my theoretical yield. 366. 2.03? 2.03 grams. Okay, that's how much we should be able to get in the lab. So the next question, if only 1.8 grams of AS2O5 is actually produced, so this is what Noah did. Oh, I just realized you're almost like sodium hydroxide. Almost. I almost wanted to write that. That's what made me see that. Can I call you NaOH? I think it's just NaOH. NaOH. All right. So, how much did he actually get in the lab? Which one is the actual yield? This is what he got experimentally. How much should he have gotten? To get the percent times 100, I'm going to say 3 sig figs because this is clearly a 3 sig fig problem. 88.7? I thought it was, okay. 88.7%. Not too bad. It's a pretty decent yield. So do we have any questions on this one? All right, let's move on to some fun stoich. This is a good problem, and I want to see who can figure it out. All right, an industrial method for the production of elemental zinc from its ore is to roast the crude ore in oxygen and then react it with carbon monoxide. The following reactions describe the chemical process. So this is a two-step reaction process, a two-step process. A 10 kilogram sample of ore containing ZNS was chemically treated according to the reactions above, producing 2.85 kilograms of zinc. Determine the percentage of zinc contained in the original sample. Don't let this scare you. It's actually not that bad. We've got ore, okay? Big piece. It's a 10 kilogram sample. Do you think we're going to leave it in kilograms, though? No. So how much is that? Isn't that 10,000 grams? So we got 10,000 grams of ore. So what is in this ore? Well, the ore does contain some ZNS, but it also contains a whole bunch of other stuff because it's not pure ZNS. There's a bunch of crap here, and a bunch of stuff here, and a bunch of other stuff here, okay? But when we take this piece through the reaction, the only thing that's going to produce the zinc here is however much ZNS we have in that ore, okay? So are you with me so far? In this process, it says we produce 2,850 grams of zinc. So 2,850 grams of this zinc. The question is asking us to determine the percentage of zinc sulfide in the original sample. Any ideas? Find ZNO, okay. How do we find ZNO? Winborn. Well, we're gonna, that's gonna happen naturally. There is a bridge connecting the two, which is ZNO. And so I'll show you that part. What I want to get right now is what's the big picture? What do we need to find? We need to go to ZNS, and we need the grams of ZNS, right? If we can get the grams of ZNS here, what will that allow us to do? Find the percent, because this is total. Our part over whole, our total is this 10,000 grams. If we could get grams of ZNS, that's part over whole times 100, right? So we just need to do Stoich through the process. And this I'll show you since you haven't really seen it this way before. You're going to see it's really, really simple. We're going to start with our 2850 grams of our zinc. We're going to Stoich. Because there's this connection, we're going to Stoich to there. That's all we can do. So for every 1 mole of ZNO, I have, oh wait, what am I doing wrong? I got to get on the mole bridge, so I got to get to moles first. So every 1 mole of zinc, I have 65.4 grams of zinc. Do you see why it's crucial that you write units down? Had I not done that and I saw that my units were canceling, I might have done the problem incorrectly. Units stop you from making silly mistakes. Now, for every, I've got a 1-to-1 relationship, 1 mole of zinc, I have 1 mole of ZNO, zinc oxide. So my moles of zinc cancel. Okay? Now this is the part that is really not that hard. There's a relationship between zinc oxide and zinc sulfide. What is it? 2 to 2. For every 2 moles of ZNO, I have 2 moles of ZNS. But am I done? No. What do I need? I need grams of ZNS. So for every 1 mole of ZNS, I have 97.48 grams. Okay, so now give me, just to 3 sig figs, how many grams of ZNS were required to produce that much zinc. It's going to be a lot. (4,250 grams of ZNS. All right, determine the percentage, part over whole, 4250 grams of ZNS divided by my 10,000 total grams of ore times 100. What is the percentage of ZNS? It's going to look like it's close to half. 42.5% ZNS. Whoops. The ore is 42.5% ZNS. That's not too bad. As long as you realize that relationship between those equations and the mole bridging that can happen, it makes it a pretty reasonable problem. Y'all ready for the big daddy sexy problem? The last one of the unit. This is a cough problem, guaranteed problem. One that you will see not only on this test, but almost guaranteed on the AP. This type of problem is using the products of combustion to help you figure out an empirical formula. Super common. There's multiple ones in your homework that you need to practice. I promise you'll see it multiple times in your few months with us. So let's go ahead and look at this. It says a 0.00300 gram sample of naphthalene, a compound containing only carbon and hydrogen, was burned in excess oxygen to give 0.0103 grams of CO2. Determine the empirical formula of naphthalene. The formula weight is blah, 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 and then determine the molecular formula. So we have to find the empirical formula. One thing, you don't need to write this down. I just want to show you this. I remember the structure of naphthalene because my high school teacher did this. And I think she had it posted, if I remember correctly. That's naphthalene. She drew this, and I have it on the side of the board there. I just did it so the audience at home can see it. So what naphthalene is 2 benzene rings hooked to each other. That's what it is. And then it was this monster looking thing, and there was this bubble coming out of his mouth that said, "I hate moths." And naphthalene is mothballs. So that's how I remembered it. So I'll never forget the structure of naphthalene. It's actually never come in handy in my life. I thought it might. No, never. It's never come up at a party or at a restaurant or. So anyway, since I know the structure, I kind of know what the molecular formula is, but we're going to pretend you don't know the structure and actually solve this problem. So we are combusting naphthalene. Naphthalene is it contains only C and H. So the thing is, I need the empirical formula. So I'm looking for those coefficients, correct? We're combusting it, and when we do, what products do we make when we combust organic compounds? CO2 and H2O. In this particular problem, they say that when they combusted 0.00300 grams of this stuff, they produced 0.0103 grams of carbon dioxide. That's all the information they give us. They say, okay, find the empirical formula, find the molecular formula. So if we're trying to find the empirical formula, what are we looking for? Okay, oxygen's in excess. But if we want to find the empirical formula, think about our table, find moles. But when we started, we usually started out with grams or percent, right? Yeah, at the end of the day, we need moles here. And then we can divide by the smallest mole. But I know we need grams, and I'll show you why we need grams. So we really need to find grams of each of these things. And that's our first step. So I'm going to say one word to you, and maybe this will strike some thought. Conservation of matter. Grams of what on the other side? We can find grams of carbon on the other side. Why? Because of the conservation of matter, carbon is produced, and it's only in the CO2, right? All the carbon in the CO2 had to come from the carbon of the naphthalene, right? So the amount of carbon in CO2 is the same as the amount of carbon in the naphthalene. Once I figure out how many grams that is, what can I figure out then? Grams of hydrogen by subtracting it from the 0.003, right? So let's do that. Let's look at just the carbon dioxide alone as its own entity. We're not going to stoich or anything like that. We're just going to say, okay, I have 0.0103 grams of CO2. Looking at CO2 within itself, I got to get to moles. So for every 1 mole of CO2, I have 44.01 grams of CO2. Well, now I'm in moles of CO2. How do I get to grams of carbon? Perfect. For every 1 mole of CO2, I have 1 mole of carbon. Are you all comfortable with that yet? So what if I were asking for moles of oxygen? For every 1 mole of CO2, there's 2 moles of O. But we want carbon, and then how do I get to grams? We could have stopped here for the empirical formula. You are correct in saying that. We could have said moles and then find the low ratio, but we need to know grams because we have to do the subtraction in grams to get the number of grams of H. So we've got to get this in grams. So that's 12.01. So how many grams? Give me lots. I know how this problem rolls. Give me lots of sig figs, lots of decimals. Perfect. That's how many grams of carbon. All right? So I'm going to start my little table. I've got 0.0028108. Nice. And then hydrogen, how many grams do I have? What am I going to do? I'm going to subtract, because the only thing in this compound is carbon and hydrogen. What'd you get? 1892? All right. Now I can do an empirical formula. I have grams. I convert grams to moles. So I'm going to divide this by 12.01, divide this by 1.01, 1.00, no, 1.01, or 00. No, it's 01, 1.01. Okay, so tell me, keep lots of decimal places here. What do we get here? .0002340.4, and what do I get here? It's going to be so close. Okay, so these are moles. Now that I have moles, how do I find the empirical formula? Divide by the smaller mole, which in this case is what? The hydrogen. So we're going to divide that by 0.0001873, giving us 1. And this is divided by 0.0001873, giving us 1.25. Nice. That worked out beautifully. Except I can't have C1.25H1 as my formula. What do I have to do? Multiply by 4. Multiply by 4, I get C5H4. That is my empirical formula. Now we're halfway done. Now they say, well, what's the molecular formula? We know that the molecular formula has a mass because they give it to us, and that molar mass is 128 AMU. What is my molecular formula? I know the empirical formula. What do I need to find? The mass of the empirical formula. I need to know this thing's mass. What is this thing's mass? 64.0.09. Look how nice this is. Ah! Oh, that scared me. I yelled. Sorry, people at home. I didn't want to extend the page. I hope I can get it back down. I'll leave it. We'll just let it go. All right. So this is very cleanly divisible by that, right? That division is 2. Since the division is 2, what is the molecular formula then? C10H8. And if we were to go back to our picture here, my mothball picture guy, you'll learn this later, and especially if you take organic, that's with carbon at each intersection. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. And then there are 8 hydrogens. There's alternating double bonds and stuff in here, but trust me, it works. Okay? Now, before I wrap this up, we have a few minutes. I want to throw another thing at you in a problem like this. And these are problems you're going to have to practice on in your homework. But what if I were to say, you know the grams of a hydrocarbon that is C, H, and O. And you're going to combust it. And you're going to make CO2 and H2O. And I'm going to give you the grams of this and the grams of this. Perfect. That was quick, Winborn. So you're going to do the same thing. You're going to find grams of carbon here, correct? Like we did here. Hydrogen, only source of water is the only place where hydrogen is produced. So all the hydrogen here is all the hydrogen here. We can't just subtract for hydrogen. Why? Because we have 2 unknowns here. So we need 2 of them to be solved in order to subtract to find the third. So we're going to find hydrogen in this one. We're going to find carbon in that one, subtract both of those from this grams to get my grams of oxygen, and then do the empirical formula from there. You will have one of these threesome things to practice here. So make sure you can do it. It's the exact same process. We're just adding on the hydrogen. Okay? All right, that's the unit, Unit 1. Now you have a few days. You have the weekend, and you have Monday and Tuesday to let this all soak in. Good job. Good job.